All right, guys, welcome to um, a class on how to carry out quantum calculations using Gaussview. So today we'll be looking at how we would carry out or how we set up our molecules for quantum calculations. We'll be looking at how we set up our molecules for quantum calculations. That is how Gaussview and Gaussian overlap. So let's take a look at that right away. All right, now let me first open the Gaussview app now. Right, take for instance, if we are asked to carry out some calculations on, let's say, propanone. Although we are not yet carrying out the calculation, I just want to walk us around the setup and then some functions that are related to the calculation setups. So I would model for propan 2-on or 2-propanone, and then would see what happens when I click on the calculation setup, and I'll walk us around some of the informations that we have there. All right, basically, let's start with the modeling. Right, we learned previously that we take this guy here, the software itself has already selected, it is already, it's already, it automatically chooses carbon, or it automatically selects carbon as a first elemental fragment on the periodic table as an element fragment, and then we have the sp3 carbon here. So I can kindly place that in this position. Right, that being done, I can come to the element fragment, select the sp2 carbon that I want. I want the single, double, trivalent fragment. I select that. Then I bring it here. Come here again. Select the oxygen molecule, maybe oxygen atom. Bring it here. Then I can come here once more. Go to carbon. Select the sp3 or the, and then now we have our 2-propanone. Now, in order to carry out the quantum or to show us the calculation setup, we can come to calculate here and then click on Gaussian calculation setup. That is one way. Another way to access the calculation setup is to just by can we can access that through a shortcut that Gaussian itself has created. And that is just to click on Control G. So that is Control plus G. You can see what we have. So let's try the first way. Come to calculate, and then we select the calculation setup. Now we can see we have lots of icons, we have lots of functionalities here. We have job type, the type of job I want to carry out, the method I want to use to take out carry out that particular job, the title of the work. I can there is a this title is for me to name the work such that I won't be confusing it with another, because if I don't title it, or place I just make some haphazard, or I just do my calculation randomly, I might be confused with the when I want to take in a data, or when I want to obtain some vital information from such a compound. So I have to title my work. So the title icon is also there. You have the link, you have the general, you have the guess, you have the population. This is pop. Then you have the PBC, you have the solvation, add input, and then preview. So let's start, or let's walk us around all of these stuffs. We want to walk us around all of these functionalities, but let's start with the job type. Under the job type, you can see that ideally Gaussian auto select the energy. There is this auto selection function. Any calculation that when you click on job type, or when job type pop up, you will first see the energy, it auto select energy. But we can see if I press on this arrow that is pointing downwards, this arrow that is pointing downward means I still have several functionalities or several operations I can perform aside the energy calculations. So I'm going to do that now. We are going to see lots more of have the energy calculation, you have the optimization calculation, you have the frequency calculation, you have the optimization calculation plus the frequency calculation, you have the IRC calculation, you have the scan, then you have the stability, and then you have the NMR calculations. So energy calculations, optimization calculation, frequency calculation, optimization plus frequency, IRC calculations, then you have the scanning for molecules, then stability, and then the nuclear magnetic resonance, the NMR. These are all calculations or quantum calculations that we can carry out on Gaussian, that is on Gaussian, that Gaussian can do. So energy, I'll take that again. Energy calculation, optimization calculation, frequency calculation, optimization plus frequency, IRC, scan, stability, and then NMR. So these are all jobs that we can perform or operations that we can perform on Gaussian. Then we can come discrete it, I mean we can come sequel to the second functionality we have, which is the method. What method or what methodology do we want to use to carry out that particular operation? So we click on method, and then under method you can see we have the same arrow is here, meaning that we have choice or we can select several approaches or several methods that we want to use to solve the problem. Firstly, is do we want the molecule in ground state? Do we want to use the Zendo? Do we want to use the CIS? Do we want to use the SACCI? Do we want to use the time dependent self consistent field? Do we want to use the TDA? Do we want to use the EOMCCSD? So these are all methodologies that we can use to carry out the some quantum calculations. So we can either choose the ground state, Zendo, CIS, SACCI, TDSCM, TDA, EOM, CCSD. So these are all, they are not just for fun. They all have meanings that can be the nature of the job that will make us know the kind of method we want to apply in solving the quantum chemical problem. So most of the time we select this ground state. Most of the time we like to calculate whenever we want to perform maybe an optimization calculation, we like our molecule to be in the ground state. So we leave it, or the method should be in the ground state. So then here we also have other methods. Here we can choose here are several methods that we can also use to carry out the quantum calculation. You have the molecular mechanics. If I select on the molecular mechanics now, you see that everything is going to change. You see the description here, the story here has already changed. So um, the molecular mechanics is just like, maybe I should walk us through that. Molecular mechanics is a very fast approach in carrying out quantum calculations. Here, bonds and atoms are treated like ball and spring. Bonds and atoms are treated like ball and spring. So in this case, we do not, in order to, in a net summary, whenever we want to carry out molecular mechanics calculation, it ignores the electrons, and then we look at the nuclei. We are looking at the nuclei interaction. We are not going to consider the electronic interaction. We are going to be looking at the nuclei interaction. So in a nutshell, the molecular mechanics approach is very fast compared to other methods that we have here. So the molecular mechanics approach is a Newtonian approach. We are applying the Newtonian mechanics in order to solve the quantum related problem. We are applying the Newtonian mechanics, and the Newtonian mechanics has to do with the application of what? That is the Hooke's law. We are treating the electrons and the bonds and the atoms, to be precise, like ball and spring. We are treating it like ball and spring. So, and here we are ignoring the electronic interaction, and we are looking at what? The nuclear interaction. So it's, which makes it very fast, and a very fast approach than every other method. But in terms of accuracy, well, it's not so accurate compared to the other counterpart. So it is the least accurate method that we can have computationally. It is the least accurate method that we can have computationally. So molecular mechanics is very fast, but the result that is obtained is less accurate. That we can, in our language in quantum mechanics, would say that it is not computationally expensive, so that it doesn't take our time. So it's very fast, and then but the results are not as accurate as we expect. So it falls under the approach. Some people classify this molecular mechanics approach under the empirical approach. So you can say it's an empirical approach. So, right. And under that, I'm going to walk us through this one after the other. We can see we have something here like the UFF. This means the universal force field. This is a method that we can use. If we want to apply this type of force field, we apply the universal force field. If we want to apply the dreading, we apply it. If we want to apply amber, we also apply amber. These are just like let me take for instance, or let me just explain it this way. You know, if you want to use Hooke's law to solve a particular Newtonian problem, you know that you are going to use Hooke's law. If you want to use like the Newton's law of motion, F is equals to ma, you know that this is the method I am going to use to solve this particular problem from your physics. So if you know a question whereby you are having force and acceleration, mass and acceleration, you should take note that okay, the nature of the method I'm going to use is going to be what? I'm going to use maybe the Newton's second law of motion. But in a question when I am having to deal with force constant and extension, I can just relate that to using what? Hooke's law. So that's the same way, depending on the nature of the problem I want to solve. That is the unique functional of the method that I am going to apply. So if I am choosing the UFF method, I know that I want to use it maybe to solve a particular problem. Grading, maybe that is the method that is best fit for the problem. And I can come here and randomly or choose at my own pace. I can choose at my own pace, or choose at my own level of expertise. So if I know that I'm also very good at using UFF, I can choose that. Grading, I can choose that. And amber, I can also choose that. So that's that about the molecular mechanics. Then let's take a look at the semi-empirical approach. The semi-empirical method is just it's a method whereby we are combining both the molecular mechanics and the and a little bit of the ab initio. So what we are trying to do here is that in the semi-empirical approach, we are dealing some, or the valence electrons. In this case, the valence electrons, are usually considered with the nuclear interaction. Valence electron interaction, that is electrons in the outermost shell and the nucleus, are what are quite important here. So here we are going to draw out, it's semi-empirical because we are making use, or it's an integration of both empirical approximations and a little bit of ab initio. So it's semi-empirical. So here we have, in this case, we have there are some already fitted parameters that would just be integrated into that particular. Let's say for instance, there are some calculated features that um when the system is running that particular algorithm, or when it's running that particular calculation, it just fits in, or parameterizes those results. It parameterizes those results or plays it into that particular data. Their library of integrals, library of variables. Whenever it is carrying out those particular calculations, it just fits it into that particular workspace, and then we get the result. Experimental, or I hope we get what I'm trying to say. So the semi-empirical method is trying to we are making use of we are considering the valence electron interaction and then the nuclear interaction. So I won't say much in that. Then we have the default spin. If you take a look at that, we can make it restricted, we can make it unrestricted, and then we can make it restricted open. Right. Then we have our choice of method too here. still this also falls under the choice of method. You can choose the parametric matrices, you can choose the PDDG, you can choose the Austin model 1, you can choose the parametric method 3, you can choose the parametric method 3 and then this maybe then you can choose Indo and then you can choose the CNDO. These are all methods that are related to the semi-empirical method. So on right, after mentioning this, let's take a look at Atrifork. Atrifork is an ab initio calculation. Atrifork is an ab initio calculation. In this case, in the case of Atrifork theory, we are making use or we are trying to calculate or we are trying to generate a single wave function. We are trying to generate a single wave function uh, for the electronic system. So here we are looking at it's an ab initio calculation. An ab initio means from the first principle. Maybe I should mention that. Ab initio calculations here means from the first phrase, is a Latin phrase that means from the start or from the beginning. That is from the first principle. So it's a calculation that involves it's a calculation whereby none of the electrons are ignored. At the same time, the nuclear interactions are also considered. So here we are looking at all possible interactions that can take place, both the electronic interactions and the nuclear interactions. Electron to nuclear interaction, nuclear to nuclear interaction, electron to electron interaction, and so many others, and so many other interactions that might have been taking place. So we are going to consider everything. So here we are looking at every of the electrons matters, but we are going to compress those electrons into a single wave function. So we are going to compress all of the possible into just one single wave function by making use of what we refer to as the Slater's determinant. These are FT calculations are quite that are quite uh, that statistical mechanics people or people that are involved in statistical mechanics kind of find it quite interesting and fascinating. So anyone that wants to learn about the Slater's determinant should go and read more on the statistical mechanics. So we have the R34 calculations, like we said, in comparison, in terms of computer expense, how expensive they are computationally. Mechanics, I mean, Artifact is computationally expensive than semi-empirical. That is, it takes more time. But the result that we are going to obtain from the Artifact method is faster, is better, and more reliable than the result that we would obtain via the semi-empirical approach and the molecular mechanics approach or the mechanical approach, the mechanics approach. So the result here is quite more accurate, but it's a trade-off. It's a trade-off, but it takes time. So it takes time to carry out the calculation, but the result that is obtained is quite better than that of the semi-empirical approach or the semi-empirical method and the molecular mechanics approach. So, and lastly, in order not to take our time, these are other functionalities. I'll just describe just four of them. Then we have the DFT. The DFT means the density functional theory. Here we are looking at the electrons, just like we are looking at this electronic system as electron cloud. You know, in the case of Artrefolk, each of the electrons are treated as in three coordinates. It would even take, so it's treated in three coordinates. So imagine if I have a system of 32 electrons, that means that I would have to treat for 96 electronic system computationally. That is 3n computationally. I would have to treat for 96 electronic system computationally. But in the case of DFT, I'm going to compress the whole of these electronic system into like an electron cloud. I am trying to like generate an electron cloud. I'm trying to look at this case, it's much more probabilistic. We are trying to look at the region or where we have the high density of electrons, where the electrons are likely to be found, and then now distributing these particular regions into three coordinates or into three geometry or into three dimensional planes. So in a case whereby I'm compressing the whole 32 electronic system into just one region, or into one place, or into one system, that can now hence be further divided into three coordinates in order to reduce my calculations, in order to reduce my the expense, in order to make it less computationally expensive, and carry out the calculations at the same time maintaining the accuracy. So right, and that's the reason why DFT is quite employed in most of the work. I was even reading a research paper currently, and I found out a trend in which DFT has been quite adopted in research work. It's an increasing trend. It has increased, should I say exponentially or linearly? It has increased linearly over the years. There is this linear increase on the rate at which how researchers have been publishing computational um, approaches or computational problems. I've been solving computational problems using the density functional theory approach. So it's just like we making use of the electron cloud. They are trying to make use of the electron cloud, and then we are locating regions or probable regions where the electrons might be, and then dividing those regions into a three coordinates, and we are carrying out those calculations. It's an also like an ab initio approach, but it's faster, and the result is unlike that of Atrifolk. In fact, better off that of Atrifolk, according to researchers. So it's far better off than that of Atrifolk. Atrifolk is more computationally expensive, and the result is not as accurate as that of DFT. It is called density functional theory because it is a function of a function. It is a function, that is why it is a unique functional. And a functional in that sense means a function of a function in mathematics, the function of the electrons and the function of the electron coordinate. So it's a function of the time in which we find, it's a function of time, at the same time a function position and a function of time. It's a function of position and a function of time of finding the electron. So it's a unique functional. So if I select on this, we can see default spin. I won't choose anything. We have the B3LYP. This means the Becquetril-Yankpa. These are all functionals that we can use to carry out the calculations. These are all functionals. Now LSDA is a LSDA it's a functional on its own. Is an LDA functional. That is the local density localized. Is it localized or the local density approximations? We also have the GGA. That is the what? I think that the GGA stands for the uh, generalized generalized gradient approximation. So the GGA stands for the generalized gradient approximations. We have the meta GGA. Those ones still supersedes that of the GGA. And then we have hybrid functional. A typical example of an hybrid functional consists of both the correlation and exchange functional. A typical example of the hybrid functional is this Becquetril-Yankpa. So the B3LYP is a typical example of an hybrid functional. So we make use of this hybrid functional most of the time. These guys are also hybrid functionals, but they are more advanced than that of the Becquetril-Yankpa. We have the correlation functional, and then we have the exchange functional. The correlational functional here is the Becquetril, while the Yankpa LYP is the exchange functional. These are all written by some mathematical descriptions. We have mathematical descriptors for people that are involved in quantum mechanics. We can read more on this particular that are interested in the mathematics and the statistical processes. We can read more on these um, correlation and exchange functionals. So the LSDA falls under the localized density approximation. I think this should be a GGA approximation. This is a GGA or a meta GGA. This is the generalized gradient approximation. While most of the time, whenever we want to carry out the DFT calculations, we use the Becquetril-Yankpa. We use the Becquetril-Yankpa because it's an hybrid functional. It's an hybrid functional. The idea behind the whole of this thing is just like a ladder that maybe I should show us something. Think it's just like a ladder. All right, just like a pyramid that leads to correctness. You know, the higher level on that pyramid, the highest level on the pyramid is the one that is closer to correctness. The one that is beneath that particular pyramid is the least correct, or the one that is far away from the correct variable. So Becquerel and pi is like on top of the pyramid. If you look at it this way, is on top of the pyramid. So it's very closer to correctness. The approximations are quite in conformity with almost experimental variables. So most of the time we use this particular Becquerel and pi to carry out the calculations. Then basis set. What are basis set? Basis set are electronic functions. These are these are set of electronic functions that we use to convert partial differential equations into ordinary algebraic expressions. We don't want to write out these integral signs, we don't want to write out the differential signs, the things that are related to the partial differential equations, and we want to convert them or merge them into, like, let's say, algebraic expressions, just like simple algebraic expressions. We are talking about the basis set. So if we take a look at things here, you see that we have a basic set that is STO3G. This STO here means the Slater type orbital. This is a Slater type orbital. A Slater type orbital. So if I select this, uh, it's different from the Gaussian type orbital, and I might not get a correct thing. The choice of basis set also describes is a unique functional or is a unique function of how accurate my calculation might be. So if I'm choosing a lower basis set, my calculation might not run very well. I might not have a very good result on my. I might not have a very good result after I have employed the best of all techniques. So I have to be very, very careful when selecting the choice of basis set. So we have STO3G. This is Slater type orbital, and then it is solving it with a three primitive Gaussian. It is solving with a three primitive Gaussian. So that's the meaning of this 3G. 3G here means three primitive Gaussian. So here, all of these ones that we can see here are all Gaussian type orbitals. Firstly, before I even discuss about this set, this this set of these codes, these codes are all Gaussian type orbitals. They are GTO. You should take note that we have the STO, Slater type orbital, when we are talking about basis sets, and then we have the Gaussian type orbital. The ones that when we have something like STO3G, we should take note that STO3G is a Slater type orbital. 321G is a Gaussian type orbital. 631G is a Gaussian type orbital. 631G prime is a Gaussian type orbital. 6311G is a Gaussian type orbital. CCPVDZ. This means correlated, consistent, polarized, uh, polarized valence, abi double zeta. Yeah, I think that's the meaning. Correlation consistent, polarized, valence, double zeta. Correlation consistent, polarized, valence, triple zeta. Correlation consistent, polarized, valence, quadruple zeta. Do you understand? I hope it's clear enough. So all of these are all basis sets that we can employ in solving our quantum problem. So 321G, what does this mean? What does this mean? What does this mean? What does this mean? This orbitals, or when we are talking about the Gaussian type orbitals, we can also split them into two. We can have the double zeta split, and then we can have the triple zeta split. So this 321G is a double zeta split. The valence electron can be splitted into the double zeta. We have the double zeta, that is the valence electron. You can split them, and that is the meaning of this 2-1. I can split them into a double zeta splitting into a double zeta split. This 631G2 is also a double zeta split. The valence electron, the 6 here stands for the fact that the core electrons are treated using the 6 primitive Gaussian functions. We treat these core electrons using the 6 primitive Gaussians, while here we are treating the core electrons using the 3 primitive Gaussians. Valence electrons are going to split into double zetas. While here The valence electron are going to split into the double zeta, while the core electrons are going to be treated using what? The cis primitive Gaussian. Same thing here. But if we take a look at there, you can see that this is a triple zeta split. Valence electrons are going to be treated triply into the triple zeta, while the core electrons are going to be treated using the cis primitive Gaussian. So, and that's clear. But most of the time, let's say I want to carry out my calculation using this. The basis said I can either choose to have these signs. This means that I am polarizing. This means, these are diffused functions. If I select on this plus, it means I'm polarizing for only the heavy atoms. I'm adding diffused functions rather to the heavy atoms. I am adding diffused functions to the heavy atoms. And the heavy atoms that we have on here are carbon and oxygen only. So it will only diffuse for carbon, 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 and oxygen atom. That is carbon, 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 and the oxygen atom that is in the workspace. So, but if I'm selecting the plus plus that we have here, as we can see, it means that I am adding diffused function for both the carbons and the hydrogens, both the heavy and the light atoms. That is carbon, carbon, oxygen, and the hydrogens that are present in the system would all be treated as would all be diffused, would all be treated as a diffused functions. It will just be, will all be diffused. So the functionality would affect both the carbons and the hydrogen. But selecting this means that the functionality will only affect the heavy atoms that are present in the system. So right, so that being said, here is the polarized function. Polarization means selecting an orbital. I am trying to increase my chances of finding the electrons within the system. So what do I do? When I want to increase the chance, I polarize over a system of orbital that is greater than the valence orbital or the valence orbital by 1. So we know that the highest orbital that we have in the carbon atom is p. So what orbital comes after the p? So if I want to select a polarized function, I select the d for the heavy atoms that we have in this molecular system. So if I also want to do the same thing for the oxygen atom, if I want to do the same thing for the other atom, let's say the light atom, now for instance, the hydrogen, I can select what? You know, hydrogen is 1s. The orbital that is coming after the s is what? Is the p. In order to increase the chances of finding the electron in the system, I will choose the p. So, and the process continues. All right, then we can come on to title. I believe everything under the methodology is very clear. We have the charge, we leave this as 0, and then we leave the spin as a singlet state. In the singlet state, we don't want it to be in a triplet, so we want the singlet state, the spin to be a singlet state. So right, then we can title our work. Here is a portion for titling our work. We can title the work, we can try to name whatever we want to name it. I can try to name it, for instance, 2-propanol, 2-propanol. So then I can highlight and let's say control P and copy. So here is for naming the compound. Here is for me to carry out some specific, is a choice for me to maybe increase the memory limit. Either choose, make a choice, can specify. I can choose the 10 megawatts, 50 megawatts, 100 megawatts, and so many other functions. And I can also try to specify on my own, so the memory limit. So then the shared processors. Here I can choose I can choose 2 processors to carry out the calculation, 3 processors, 4 processors. But it's always advisable when you're carrying out, when you are choosing those 4 processors, your system might be very slow. The reason being that the maximum amount of processors I have on the system that this system can use is 4. So I can, if I select on 4 processors, it means I'm using all the processors, all the microprocessors to carry out the quantum calculations, and operations on my system might be very slow if I want to use it to carry out any other operation. So let's assume we choose 2 processors, right? And in Gaussview or Gaussian, after Gaussian finishes calculating out the calculations, 2 files can be generated. We have the checkpoint file and then the log file. We'll still work us around that. So the chk file, that's what we mean by the checkpoint file. The checkpoint file is what is abbreviated as the chk file. We are going to take a look at the difference in subsequent videos between the chk file and the log file. So we have the old chk file here, read write file, and then lambda workers. So here we are told not to use, don't use, and then we can specify. There is a set of options that we have, but most of the time we don't really use these guys that we see here. Mostly what I need to do is most of the time I base my calculations on either whenever I want to select, I only select what has to do with the memory limit and the shared processors. Then general, we can come here to tick some things if we know we need to tick one or two things. Maybe we want to use the quadratically convergent set consistent field. If we want to ignore symmetry, we can choose that. Write Cartesians, if we want to uncheck these boxes, we can uncheck them. If we want to check them, depending on what we want to do and depending on the work, we can check them. If you want to compute polarizabilities, you can compute. If you want to use, we can just come here and then select. So it's Gaussian has given us that privilege. So then we can guess, we can come to guess options. You can mix your HOMO with the LUMO. You can only do guess, no self-consistent field. Then you can save the orbitals to the checkpoint file. You can always generate guess in optimization and localize orbitals. So these are all functions that are here. So with guess method, you can choose co-Hamiltonian, extended O'Keefe, checkpoint file read. So these are all um methods that can be employed. This is the population. I think this is the population. The POP I think stands for population, level of output, Coleman, electrostatic potential charges, natural transition of orbitals. We have the natural bonding orbitals. I think this is the NBU. I think this should be the natural bonding orbitals. We can go through all of this, but most of the time, I don't used to use this particular part. I don't deal with this part. Then we have the PVC, then we have the solvation. Solvation means if you want to add a solvent, if you want to add a solvent. So I think when I wanted to do mine, I think I chose the CPCM model, and then you can now select based on the choice of solvent that is there. So we have none. If you know you don't want to use any solvent and you want to carry it out or the problem out in a gas phase, you choose non default. IEF, PCM, SMD, IPCM model. I think let's try to work us around this. So CPCM, if I choose the CPCM, I can come here and choose. Look at, we have a wide range of solvents that we can use to carry out the calculations like heptane, others, cyclohexane, tetrachloromethane, benzene, toluene, dimethyl and lot more typical different examples of solvents. So we can choose that, then add input, and then if you want to add additional key information or maybe you want to add some other things to it, you can put that there and then preview. You can check here, you can check out the nature of your work, the work that you want to do. What are the methods that you want to adopt to solve the problem? You can see I have the Becquerel fire, the choice of basis set, polarizing the d orbital against the p, that is CRF. So these are all the necessary things that we ought to know about how we set up our molecules for calculations. So let's walk us around it once again. We have the job type, we have the method, we have the title, we have the link, we have the general, we have the guess, we have the pop, we have the solvation, we have the add input, and then we have the preview. So next class or in the next tutorial video, we are going to show us how we carry out a complete quantum calculations and things that are connected or what we do after those calculations. Thank you.